on this computer. Okay, and as far as so I just want to talk about a couple things. So as far as the exams, I'm going to work on grading them tonight and tomorrow. So you should get your grade tonight, this upcoming Friday, just in time for midterm grades. Again, my grading pulse, and again, my grading is never final. I am a human. I make human errors. So please, if you have objections to the way I grade, let me know, because it's possible I misinterpreted something. I don't copy everybody's code and test it. I work out the logic of it. So it's because that's actually a bit quicker for me. And I try to do this as quickly as possible. So it's possible I'm wrong. It happens. I'm human. And I'm happy to be wrong in those cases. Okay, next, what was I talking about earlier? I was talking about Voronoi tessellations, which sounds really hard, right? Things sound hard, especially when they come up with those names that you can't spell. Voronoi, V-O-R-O-N-O-I. Especially when you use the word tessellation, that makes it sound really complicated. But a Voronoi tessellation or Voronoi diagram is actually not that hard. The objective of a Voronoi tessellation is, you see all these points on this 2D space. Take the space around each of those points and color it, and each space gets colored, and you color each space a different. You color the space a different color based on what point it's closest to. So all the area in the space that is closest to this point is colored this color. And then all the area in this next to this point is called this color. Basically, you're saying, okay, basically, if you were to divide things geographically between centers of masses or centers of something, how would that get divvied up, right? So it sounds really hard, but I mean, like, you could probably set a talented middle schooler to coloring it, and they'd be able to do it just, do a good job of it. The algorithms, of course, of doing these are actually really tough. But this is via Euclidean distance. You can use different distance algorithms for this. Part of my research of what I did in my PhD research was kind of hilarious, where basically I was showing that distributed hash tables are equivalent to Voronoi tessellations. You can of some kind of search space, and I got a lot of responses of, well, that's obvious. And I'm like, if it's so obvious, then why hasn't it been published yet? So, but it is obvious once you declare it and see it. What's cool though is also that it is dual to the problem of Delaunay triangulation. What the heck does that mean? Well, we've got this other problem which has circles, and I'm not going to bother explaining it right now, except to tell you that basically, if you solve this problem, this Voronoi tessellation problem, you get the Delaunay triangulation for free, which is to say that basically that solving one problem automatically gets you the answer to a different problem. And this is a very cool concept that you can come up sometimes. Sometimes solving one problem gives you a problem in another area. It's also why it's important to try to, branch out if you're scientifically inclined to other sciences. I did a lot of work with the astrophysics department at my university during grad school, doing some stuff that was basic for me but hard for them. But they were doing things that were hard for me and basic for them, So, but one thing I found is that in their physics paper is that there's this operation called the Fourier transformation, which is all about frequency and stuff, and making frequency observations based off of making a frequency chart based off of observations you take. Except a lot of the algorithms for the Fourier transform, it requires that you have evenly spaced observations. But astronomers can't do that because they have a sun in the way, and then there's clouds, and sometimes there's other objects covering the stuff that you're observing, which makes it tricky. So you can't always have evenly spaced observations. So they have different algorithms to do with that, which is And it's like, well, I've never got exposed to this in computer science. I was always under the assumption that you had to have this, otherwise the problem was impossible. But in this other line of research, it's, it's standard. So, branch out, have fun. If you're interested in space, take an astronomy course. If you're interested in biology and DNA and medicine, take some biochemistry courses. It's worth it. And if you're interested in more on like how do people use computers, what is incorrectly called soft science, because it's not. You just have more unknown unknowns. Which in a lot of ways makes it harder, because humans trying to observe how humans behave, you're working with the human brain, so you're already at a disadvantage of trying to figure out how that's going to work. We have an entire field based on that, human computer interaction. That's an amazing field, and you should take a look at it if you're excited, if you're like that. And of course, if you're like me and you love video games and you love puzzles, then take a look at puzzles and stuff and try to solve puzzles. God knows there's been enough papers showing things about Mario or Tetris or stuff like that. So we're going to take a look at one of my favorite puzzles of all time today. That was a pretty awesome segue, right? So we're going to go ahead and look at the towers of Hanoi, also known as the towers of Brahma or Lucas's tower. And this is the picture that you typically see associated with the towers of Hanoi. This is an 8-disc towers of Hanoi. 3 pegs, multiple discs, okay? So the object of the game is that we want to move all the discs from this stack, from this peg to this peg. And you're like, okay, that's a pretty objective. Shoink, boom, we're done, right? So there's other rules, obviously, because otherwise we couldn't do that. So there's another rule which says we can only move 1 disc at a time. Okay. And you're like, okay, well, that's not too hard. I'm going to treat each of these pegs as a stack now. So I'm just going to pop everything off into the middle stack. And now the stack's all upside down. Sorry, it's all upside down. And now I'm going to pop everything off onto the 3rd stack. And now it's been replicated and we're done, right? So we have the 3rd rule, because otherwise it'd be simple. And the 3rd rule states, well, you can't put anything a disk that is bigger on top of a smaller disk. And it's at this point where you should be going, oh, you're kidding me, or for crying out loud, or more absurdly strong language. So there are solutions. So, and it can be done. You just simply have to move your disks around in a specific manner. Now, I did not bring my Towers of Hanoi puzzle with me because it's tiny. But I have a video on YouTube where I go into very good detail about it. Hey, does it come up for me yet? Hey, it does. That's cool. Finally, when it goes for Professor Rosen, it's coming to me. Or at least if I'm searching for me, it's coming to me. That's cool. We'd go for other Rosens other time. It's not exactly the most uncommon name. So, searching for Hanoi. They've done a number of these in time. So I've done this a number of times, but let's go ahead and look at my recursion videos. And we'll look at the Towers of Hanoi over here. Okay, just for a second, if you'll tolerate me. And if you've seen this already, sorry. Yeah, I've already gone over that part, man. Okay, so. Sorry. So the entire point of this is that basically that each problem is actually a recursive puzzle. And the idea here is that, okay, consider the objective of just moving a single disk.
Right? Not too much to go on, right? When confronting a hard problem that can
be broken up into multiple subproblems. You should probably take a look at the easiest case, our base case, moving a single disk from one peg to another peg. All right. So what about if we had two disks? You can kind of figure it out for yourself. Maybe we take this top disk, move it to the second peg, take this other disk, move it over here, and then take this disk and move it over here, right? Not too hard, not too much to think about in the problem solving process. So let's take a look at the more classical problem, which is 3. Okay? And 3 is a bit trickier, but you can probably reason it out at these steps, right? You go, okay, you'll eventually land on the strategy of doing this, which is this over here, move this over here. But the challenge is being able to generalize this problem solving process. Because what did we effectively do? Let's take a look. Our goal was that we needed to move this third disk over to here so that we can move these top 2 disks on top of it, right? We needed to get these out 2 guys out of the way. So this could go over here and these 2 could go on top. That was our problem, right? That's what makes it a bit trickier over 2. So we needed to move 2 disks from the top of this peg to here so that we can move the third disk over to here. So how do we do that? Well, to move the 2 disks over to here, we need to take this top disk and move it out of the way so we can move this disk over here. And then we can move this stack of 2 back on top. This becomes more apparent when we move to our 4 disks. Now 4 disks is where the recursion and understanding it really becomes necessary. So, how do we move 4 disks over? The steps are a lot. In fact, it takes 15 steps for us to move these 4 disks over. So, how do we move our 4 disks over? Well, ideally, we can kind of break this down into 3 parts. We can take the top 3 disks and move them over here, and then take this bottom disk, move it over here. That's our second step. And third step, take these 3 disks and move them on top. Voila. But we can't move more than 1 disk at a time. So for this problem, we need to take these 3 disks, move them over to here. It's really hard to interrupt myself. So how do we move these 3 disks over to here? Well, to do so, we need to take this disk and move it over here, but we have to do that by moving these 2 guys out of the way. So we can move this over here. So in essence, the way this problem works, the Towers of Hanoi problem works as a recursive solution, is that moving a disk here is one of my favorite. This is like one of the reasons why I love Wikipedia, because you're like, oh, it's an image. That's so exciting, Professor Rosen. Well, no, if I go to it though, it's actually, if I click on it, it's actually a bit more than an image. It's a flow chart, which may be a bit hard to see here. So we look at this as our end goal. We want to move 4 disks from the first peg to the second peg, sorry, to the third peg. And the way to do that is as follows. We need to move the top 3 disks out of the way, then move the last one, to where it's going to go. And we want to move then we move the top 3 disks back on. So how do we move 3 disks? Right? How do we move these 3 disks? Well, we need to move a stack of 3 over to the middle. We move a stack of 2 over to the far, move the bottom of this 3 stack, then move this 2 to the far. And how do you move a pile of stack 2? Well, you move a pile of stack 1 over here, you move the bottom over, and then you move a pile of stack 1 on top. And so we can see basically that so we can kind of get a glance of the code. And the code is, well, the pseudocode is actually fairly straightforward. The pseudocode is actually fairly straightforward, which is solve. So I'm gonna go, we're gonna move n disks from source to destination, okay? And we're gonna move them, and then we have a auxiliary stack, a third one, right? These are all stacks or lists or whatever. Okay, so how do I solve this? Well, if n is greater than 1, in other words, if n is greater than or equal to 1, in other words, if there's disks to move, right? What I'm going to do is I'm going to, in order to do this, I have to move n minus 1 disks from the source out of the way onto auxiliary stack, right? And go to the destination. And then I need to move this 1 disk out of the way, which means that I have to do what? I need to do n dot. So I need to do destination dot push n dot, sorry, not n dot pop, source dot pop. Right, something like that. And then I'll just take, and now that I've moved these things out of the way, I need to do sorry, mixed everything up. So now I've moved my bottom disk from the source to the destination. And to do that, I moved everything out of the way and put it on the auxiliary stack. So what I need to do is move those n-1s from the auxiliary stack to the destination. And that means that the source one is going to be the storage space for this particular move, right? Okay, and that's it. That's actually, that's all the pseudocode there is. And you might be going, okay, Professor Rosen, but there's no way that in actual code that this would work. And I'd say you're 100% right. In order for it to work, I'd have to add a def statement and change push to append. And now we'd have a working Python program. Okay, and if you're not, and if you don't believe me, here's the Python program that I've had memorized essentially from multiple years ago because it is that short. And I can run it and show you that it runs. And yes, I trust this workspace. No, I don't need to debug. I just need to run it. Can you run it for me, please? Run. Yeah, there we go. And it shows and it's a bit tiny to see on my screen, but you can see all the respective moves over here. And this works. Now, mind you, it requires 2 to the nth minus 1 moves. So 2 to the n disks, that amount minus 1. So 3 disks require 7 moves, 4 require 15, right? 16 minus 1. So this horrific thing will probably never be able to actually be solved because that's a lot of disks. And, 30, remember, getting up into the 32, 31 range, we get just into the billion, But it is pretty awesome that there. A lot of museums do happen to have one. I even stumbled across one in one of the science museums I went to when I was in Tokyo, which is pretty awesome. There are also a number of other ways to view it, which are really interesting. There's also a number of awesome variations. Bicolor. So here, where basically we're given 2 disks with intermixed colors, but then we want to get it into this configuration. So we want to start with this and then with this, which is pretty crazy. There's also an awesome Project Euler program that one day I'm going to actually sit down and try to tackle, which is called Drunken Towers of Hanoi. Yeah, so it's pretty far up there. And it is basically Towers of Hanoi, but you've got a drunk mathematician who goes back and forth between these certain number of spaces, and because he's inebriated, he can't control his movements, other than picking up and placing down, but he can't control but he's got a 50-50 chance of which way direction he goes. So give us the last 9 digits of the number of moves it takes for this amount. So it's basically solving mathematically how many optimal moves it's going to take, which is pretty interesting. So what I'd like us to do today is I'd like you to take a couple minutes and try to do this, which I closed sillily enough. Take this Hours of Hanoi and program a solution in Java. I would just take 10 minutes and try to program this and do this in Java using stacks. Now the issue here is that stacks might be the trick for you to print out if you're using my stacks or baked in linked lists. Well, if you do lists, it should work, right? And linked list, you have all the stack operations baked into them, I believe, because they implement stack. But I'd like you to try to take this code and put it into an actual working configuration. And I'll go into Canvas and make a Dropbox for it and check and give you some points for it. So if you've got your laptop, great. If you don't get your laptop, get socially distantly close to somebody who does and work on it with somebody else. And feel free to work on somebody else as well with this for somebody else. Again, this shouldn't take more than 10 minutes. So, so give me a second to create a modules. And I'll make an assignment for it. In 1 sec, a Dropbox for it. So an assignment, create assignment, because I thought there was one in the other ones. New assignment, towers in class. Okay, add item, edit assignment, and I will publish it. It will be under the recursion modules. So points, let's go ahead and put it into your assignments. It will be, because it should only take 10 minutes, so I think it's worth 10 points. So that will help keep your average up on this, especially if you have to turn something in late submission type online. If you have no idea what this is, refer to the 1007 lecture. Save. Text entry or file upload. So you can even just copy paste your code in. Okay. So there you go. There's the code if you want to try to get it. So, but part of this exercise is to get you to see that a problem like this is to emphasize something. Recursion makes things like magical. It doesn't seem like this should work, but it does, because it allows us to kind of break into that kind of weird cross-section of mathematics and linguistics that allow us to really express a whole lot in a single statement. Now, for those of you who are unfamiliar with Python, here's what's going on over here with A, B, and C. They're declaring in what would be Java 3 static lists, or 3 lists that would be declared in main. Either interpretation of that is correct. Python does not have arrays. It only has lists. Specifically, it only has array lists, and these is what they will, and that is how you make them. You make them like you would arrays in other languages. So that is what's going on there. Python also doesn't have types, or doesn't have strong types. It has what's called duck typing, which means that if the variable looks like a duck, quacks like a duck, moves like a duck, then it's a duck. So it figures it, so it's dynamic typing. It figures out what it is when it needs to figure it out. And so it seems weird, but basically everything over here and everything over here That's essentially what you would see in main. And then this def, that is what it is. That's just simply define function, which is creating a method. And I think you should be able to figure out what print means. Print means to print it out. This thing sep equals /n. So their print, the way it works is that you can take in any number of arguments and you will separate them by spaces by default. Here it's saying, I don't want them separated. I don't want these arguments separated by spaces. I want them separated by new lines. So you can see here that Python is a very concise and powerful language with a lot of the optional abilities that can make it a lot more concise. Append here is just simply adding on to the end of a list. That is their special method for add to zero. Add to index size. And once you're done with this, you can, ask for help on other stuff or demos, or you can ask for help with this if you're having trouble with this. So much coughing. Everybody's making me super nervous. basically the only things that can't be imitated in one line in Java is this print line, which you would just have to separate into 4 separate print lines. Where you print each of the stacks. These would just be, new line, and then this one, yeah, you'd probably just create it by adding the items 3, 2, and 1 into A in main, and then again passing them into your main method. There is a new assignment that I just created on data structures. It should be under assignments and also under modules. So if you go to module 6, there is a towers in class exercise. I'm also going to move it into the appropriate place for assignments so that it gets to the appropriate location. Yeah, it's already there. So if you also check out your assignments, it'll be right before recursion is due. Meanwhile, if you finish up the recursion work, don't necessarily go onto the index tree next. I plan on I'm going to see if I can't revise it over the weekend to make it a more interesting problem than it has been in the past. I might decide I'm going to be tempted to use the time to create a I'm going to be going through basically and figuring out the latter half of the semester and the due dates for everything this upcoming weekend. Because a lot of stuff is just automatically adjusted and I have to readjust that. Yeah, sorry. That's the issue. I get so easily distracted. Okay. File. Yes. Mhm.
Extra functions like remove class, for example. We're going to try to call it and using the activity and looking at a long activity. Could be. Although, let's see.
Oh, well, it's because you called them as a list. As opposed to a linked list.
Oh, okay, I have to call them as a link list.
Yes. That is my hypothesis.
Thank you.
All right, I'm typing up my solution right now. Should be done in about 2 minutes. Like I literally just started, so. now. Okay. And all I have left now is the print statements. So. That's how I can't print them out like that. Okay, so I guess I am gonna make them statics. Hmm. Oh no, I was mixing up stacks and queues, believe it or not, for what they could do for their inheritance structure at least. So Okay, so with some variation, this is essentially what you should have. However, I'm guessing that some of you may have had issues with printing stacks. Yes or no? No? What was the issue? That you ran into? I'm interested because there are, despite it being simple, there are a couple headaches and hiccups you can hit. Yes. Cannot resolve what method?
I just put like so and then like the three things.
So let's go ahead and print line A and let's see what happens when I run solve. Solve 3 source, sorry, 3A, C, B. Again, notice that I've declared everything outside of main over here. And I'm just printing out what's going to be an A, which is going to be repetitive, I'm sure. Yep. So I'm not sure specifically where. I'll take a look at what you have. One thing that throws me off almost every time, except for the fact I'm looking for it, is that you've got source, destination, and you stack, and you have ABC. But here we want to print out ABC rather than source, destination, stack. Because what the source is, the destination, and the auxiliary are change every time you call the method. So that's why we have these global variables over here to look at. If that am I making sense or am I speaking gibberish? So that's why I have these things as static methods so that we can refer to them. And so that's why I have. So here I would just be able to do A, B, C. Except in one line,
Yeah.
with the new lines and stuff.
Yeah.
Yeah, I like using copy paste. So makes me feel powerful. My ego needs as much boosting as possible. And so then we can just simply do a lot of lines like this and print it out. And now we've got a full solution. And we can now see how that works. Of course, printing it out vertically is so interestingly enough, like you think, solving towers isn't always the easy part. But then if I said, okay, well, now I'd like you to print it out vertically, right? So that rather than looking at it so that the stacks are laying on their side and we've got 3, 2, and blank and nothing. The idea of tilting it, which I'm not going to do here, just consider that like it's sometimes very hard to explain why doing some things is more difficult. Oh yeah, solving this puzzle totally easily. Rendering the printing, that's going to take me a couple hours to figure out just how to print out this solution at every step if I wanted to represent it vertically, because you'd want to get your indenting right, and also you'd have to iterate through the stack, right? To print out everything in the stack. So it ends up being quite the, and then you'd have to know how big things are. You'd have to use auxiliary data structures. It would be a mess just to try to get it to print, vertically in a way that normal humans would look at it. And we'll see this as well when we look at trees. When we're trying to print out trees, I'm going to use a really confounding method to print out my trees that I grabbed from our textbook, just simply so that I could print out and it looks like it's in some kind of layered, orientation. Otherwise, you're going to rely on me drawing poorly a whole lot. So, all right. So otherwise, that's what I have for today. There's any questions, you can go ahead and start demoing stuff to me or ask me for help. First, I'm going to go back there and see what the heck blew up there.